Good morning, students. Am I audible? Good morning, everyone. Am I audible?
Yes, sir.
Just give me a minute. We'll get started. Yeah. Good morning, guys. Are you able to see my screen?
Yes, sir.
Okay.
Sir, it's just showing black screen. Can't see that.
It's showing us.
It's showing a black screen. It's just learning room I started pressing.
Okay. No,
No, sir.
it's the same case. Now also, is it the same case?
Yes, sir. Showing same.
Yes, sir. It's showing class learning room has started screen sharing, but nothing is good.
Is it happening? No,
Yes, sir.
you're able to see my screen, no?
Yes, sir.
Okay. Like, what is visible to you? Is it the PPT?
Yes, sir.
Okay. Okay. So we shall get started with this. So last class I was discussing about, sorry. Last class I was discussing about the errors, right? And I told you whenever you do a measurement, you're going to get an error, right? And we saw how to, like I told you, there are methods to measure these errors depending on the physical quantity. But you know what? As per your syllabus, the method of calculation of errors is actually deleted. So what I thought is before holidays, first I'll complete as per your syllabus. And for those errors and everything, I can give you the pre-recorded content, which is already there in the app. Okay, that part alone, I'll cut and give it to you so that you can have a look at it because it is out of your syllabus and it is only for your knowledge. Is the point clear?
Yes, sir.
Right. So having said this, we will get started with the next important concept, that is significant figures. Okay. Some problem with my device. Wait for a minute. I'll do one thing. I'm not able to write on this. Just give me a minute. Nonsense. Really sorry, guys. Yeah. So the next topic that we are going to see is significant figures, right? So whenever you make any measurement, right? Whenever you take any measurement, like as we discussed in the previous classes, we know that we need to report the answer to certain decimal values. For example, let's say I'm asking you to measure the length of this pen, right? So depending on the device that you're going to use, you'll be able to report the answer in terms of multiple decimal values. For example, some of you might report the answer as 10.2 centimeter. Some of you might report the answer as 10.25 centimeter. Some of you might report the answer as 10.252 centimeter. So depending on how you are representing the answer, right? Depending on how you are going to represent the answer, it has something to speak about the precision, right? Before I proceed, I want everybody's video to be on. Yes. Raghav, yours? Okay. So listen. So when you take a measurement, right, there are certain things that you are going to calculate. So what are they? They are going to have the number of digits, right, about which we will be certain. So what do you mean by certain? About which we are sure that this is the answer. If you look at all the three answers that were reported, this 10.2 was constant. The first two that is appearing after the first decimal is a constant. After that, depending on the instrument that we have in our hand, different people were able to report different answer like 10.2, 10.25, 10.252 like this, right? So if you look at how to measure the number of significant figures, when I say significant figures, we talk about the number of digits in that measurement, which is helping us to make a decision, right? So the number of digits in a measurement about which we are certain plus one additional digit about which we are uncertain. So the sum of the number of these digits which are certain plus one uncertain digit is what is called as the number of significant figures of that particular measurement. Are you able to get a perspective out of this? Right. So when you take a measurement, there will be certain digits plus one uncertain digit. So all these digits put together is what we call it as significant figures. So make a note of the definition. Let me know once you're done. Okay. So I hope it is clear. Shall I proceed? Shall I? Yes. So listen, the question is, if I give you a particular measurement, see, all that I'm going to ask you is to find the number of find the number of significant figures that are there in the measurement that I gave. For which, for us to get the same answer universally, there are certain rules that are designed, right? And the rules are like this. If you look at the first rule, all the non-zero digits are significant. So the first rule is all the non-zero digits are significant. So what is the meaning of this? For example, if you take a measurement, let's take an example like this. If you take a measurement like this, where it says it is 125.63 gram, right? So here, all the digits that are there are non-zero, right? So what is going to be the number of significant digits in this?
5.
It is going to be 5. So what are the 5 significant figures? They are 1, 2,
5, 6,
5,
3.
6, and 3. Right. So this is the first rule. So concentrate. I'll share the slide with you. You need not focus more on writing. So concentrate on understanding the concept. Second, all the zeros between two non-zero digits are significant no matter where the decimal point is. If at all it is existing, right? If at all I have a measurement where I have a decimal existing or not existing, but I have multiple zeros between two non-zero digits. So those zeros will become significant. For example, if I take the measurement like this, 125.004 centimeter, right? Then I will take something like this, 125.004 like millimeter, for instance. Okay. So what is the answer for this?
6 significant figures.
So here there are 6 significant figures. Here also you have 6 significant figures. Reason?
We don't consider the decimal point here.
Yes, we need not consider the decimal point at all. We need not consider the decimal point at all. So all the zeros which are existing between two non-zero digits are considered to be significant itself because they are going to increase the length of that value. Right? Hence they are significant only. And the third point is if the number is less than 1, then the zeros that are on the right of the decimal point, but on the left of the first non-zero digit are not significant. For example, whenever a number is less than 1, its value always starts as 0 point something. Suppose I have something like this, 0.000157. Okay. Then if I count the number of digits, see 1, 2, 3, 4, 5, 6, 7. I have 7 digits, but are all the 7 digits significant? Are they going to help us understand something? No, that is the meaning. So what the statement says is that the number is less than 1 means if it is starting as 0 point something, right? Then the zeros on the right of the decimal point, but to the left of the first non-zero digit are not significant. So these 4 zeros are not going to be significant. So out of the 7 digits, we have only 4 significant figures.
Sir, 3.
Sir, 3, right?
Sorry, we have 3. We have 3 significant figures because 4 are lost. Am I clear with this? Next. In a number without decimal point, okay, there is a number, there is no decimal point at all. The zeros on the right side of the last non-zero digit are not significant. So if I have a number which does not have a decimal number, which does not have a decimal point, the zeros on the right of the last non-zero digit are considered to be not significant. For example, if I take this 132, if I take 1320, if I take 13200, and if I take 132000, right? In all these examples, what is that you can consider? Here, the number of significant figures are 3. Here, how many are the significant figures?
3.
Here also it is 3 only, because it is a non-decimal number. Any zero which is considered after the last non-zero digit is not significant. But when will the zero become significant? If there is a non-zero digit which is there after the zero, then it will become significant according to the second point. You're able to understand? So here also it is 3, and here also it is going to be 3 only. I hope it is clear. Right? So the last point is the trailing zero in a number with decimal point are significant. Meaning, if I have a number like this 7.90, if I have 7.900, 7.9000, so in this case, what are the number of significant figures here?
3, sir.
3.
And what are the number of significant figures here?
4.
They are 4. And what are the number of significant figures here? It is 5.
5.
What is the reason for it? Because, see, though, if at all I am reporting a measurement like this, generally when you do an experiment, right, you repeat the experiment multiple times. Maybe one of the times you got the answer as 7.90. So the meaning of this is, maybe next time you are going to tell me a reading which is giving the value up to 2 decimal points. Meaning the next reading could have been 7.92. Who knows? Instead of this, in the first case, had you written it as only 7.9, the second case also you would have written it only as 7.9, because you are restricting the value to 1 decimal point. Means you are cutting the more precision that is possible. That is the reason why the zero in this case is important. Whereas in this case, the zero is not important because it is all a multiplication factor. It is getting converted to exponent, meaning the first one is 132 into 10 power 0. In the second case, it is 132 into 10 power 1. In the third case, it is 132 into 10 power 2. Fourth case, 132 into 10 power 3. So these are the significant figures which are decided. These 3 are giving me the values. Meaning, I could have established the same reading in multiple systems of unit. For example, if I had represented this in terms of meter, I would have written the same reading here in terms of meter, which is also 132 kilometer. So which is helping me understand? It is only the first 3 digits, which is there before the zero starts, is helping me to understand the reading. That is why in this case, the zeros after the non-zero digit are not considered to be significant, whereas in the fifth case, they are considered to be significant. I hope it is clear. The logic is clear now, right?
Sir, what if it's 79.00?
79.001.
Yes, sir.
Those 2 zeros are important. So it is 4. They are 4. Did you understand why it is 4? Because you're trying to tell me one thing by by you reporting the answer as 79.00, you're trying to tell me something. What is it you're trying to tell me? First of all, you have an instrument in your hand which is able to measure up to 2 decimal values. Means I will understand you have something precise depending on what we have at that point of time. Let's say I have a device in my hand which is able to measure only till 1 decimal value, but you reporting the answer as 79.00, you're telling me that my next reading, there is a possibility that I'll get 2 non-zero numbers also. That is why these zeros are important. So the main reason why we study the significant figures is to decide the precision. I told you about precision, you remember? So precision is decided by the measuring instrument. But you know that all the measurements are going to be dealt in terms of numbers. So it is important for us to understand, like, what numbers am I supposed to report in my final answer? So those numbers are given like a name called as significant figures. That's it. That is all we are doing. I hope you're clear, no? So this is a very, very important point, not only theoretically, but when you're doing the experimental lab also, you need to be clear and precise with what is the kind of measuring instrument you have in your hand and up to how many decimal values are you supposed to report the answer. So if you're not clear, you need to ask your teacher on how many decimal values are you expecting from me. Is that point clear? So these are all the points you need to take it to your lab as well. Clear? So these are the rules to find the number of significant figures. So the next question is about rounding them off. Right? There are certain instances where we will round off certain values when we report the final answer. So let's see what are the rules to be followed when we are rounding off. So what do you mean by rounding off? You're going to drop a number. The final digit you're going to drop, and based on the final number's value, you're going to make certain decisions. Right? So for that, if the insignificant digit, I told you, every significant figure has certain and the uncertain value. If that uncertain number which you want to drop, right? If the insignificant digit to be dropped is less than 5, then the preceding digit is left unchanged. This is what you have been practicing throughout. This you already know. Okay. See, for example, if I have the reading as 10.743, now I want this to be rounded off to 3 significant digits. So what is the number you are going to drop? You're going to drop 43. So look at the number. So if you consider this to be the insignificant figure, then what is the number preceding to 4? It is 7. And the number you're trying to drop is the number which is less than 5. Hence, you will report this answer as 10.7. That is the meaning of the first statement. Am I clear with this? Now, the next possibility is you might be in a situation where the digit you want to drop is a number greater than 5. If that is the case, then you need to increase the preceding number by 1. For example, if I have a reading as 10.68 and I'm asking you to report it to 3 significant figures, meaning you will take 1, 0, and 6. So what is the number you're going to drop? You're going to drop 8. So if you look at the number you're dropping, it is greater than 5. So what are you supposed to do to the preceding number? You increase it by 1. Here the answer will be 10.7. Am I clear with this? Right. So what did we see? When you want to round off, you either drop the number which is less than 5. So less than 5 means the preceding number is unchanged. Greater than 5 means the preceding number is increased by 1. But what if the number that you want to drop is 5 itself? That is the third possibility, right? So if the digit to be dropped is 5, then the preceding digit is increased by 1 if it is odd. Whereas if it is even, it is left unchanged. For example, I have 10.743. 45, I have 10.55. So each of the readings that I gave you has 4 significant figures. I'm saying report the answer to 3 significant figures. So you're going to drop the last digit. In both the cases, if you observe, the last digit is 5. So here, how am I supposed to report the answer? The preceding number is left unchanged.
10.4.
The preceding number is left unchanged,
If it is even, sir.
even. Whereas in this case, the preceding number is increased by 1,
10.4.
odd. So that will be the answer.
Sir, but why, sir? Why we change if it is even and odd?
Just to follow
report the
universal
even
pattern.
answer.
Just to follow universal pattern.
Okay.
I told you, these are whenever a rule is formed. Cricket ஆடுறப்ப ஏன் பால் இப்படி தான் பிடிக்கணும்னு ரூல் இருக்கு. One pitch கூட பிடிச்சிருக்கலாமே. Somebody has framed the rules. This is how you need to play the game. You are doing it universal. அதே லாஜிக் தான்.
Okay, sir.
நம்ம ஆடும்போது என்ன பண்ணுவோம், செவர்ல அடிச்சா 1 run 1G 1 granted எல்லாம் சொல்றாங்க. So அது மாதிரி we frame the rules. புரியுதா? Somebody has done it, we are just applying it so that we are on the same page. அவ்வளவுதான். புரியுதா? Am I clear with this, guys? This is a very important topic. I think you would have learned the same thing in your chemistry also.
Yes, sir.
The first chapter, stoichiometry, you would have learned it, the mole concept. And
Yes,
there
exactly.
also,
We studied the same.
yeah, there also you need these numbers because there also you're doing.
Sir, is it the exact same or it will be different? I
Almost the
think
same.
it's okay.
But see, you just do the comparison. I've not gone deep into the chemistry aspect.
It's the same only, sir, but I don't know if it is exactly the same.
Just have a look at it. It should be mostly same because all we are
It's
dealing with
mostly
is
same.
numbers. It is numbers, irrespective of whether it is chemistry or physics. The numbers are same, right? Ultimately, you're doing a measurement. You're going to report the answer. That's it. I hope this point is clear, right? So first, what we saw is we tried to understand what are significant figures. Then we understood what are the rules to be followed to find the significant figures. Then we understood how to do the rounding off. Right. The next question is about what if I'm put in a situation where I need to report the number of significant figures. I need to report my answer to a specific set of significant figures where I am asked to add or subtract 2 readings. We need to understand this. So addition or subtraction of 2 significant figures. That's what the next concept is. So let's understand this. See, the following point should be observed while carrying out the addition or subtraction of 2 significant figures. If all the numbers are integers, the summation or subtraction should be carried out in a normal way. You're not going to worry about it. If all the numbers are integers, you're just going to add them or subtract them like how you do every time, right? But the challenge starts only when you have this decimal and where the zeros are placed, right? So in addition or subtraction, when you're reporting the final result, the final result should retain as many decimal places as that is there in the number with the least decimal places. I'll tell you what is the meaning of. Okay, so let's take an example. For example, I have an experiment where I ask you to measure the resistance of a particular device. Okay, so let's say you are obviously going to report the answer to me based on the kind of measuring device you have in your hand. Let's say the first reading is coming out to be, let's say 18.715. So you have a more precise device in your hand, right? And let's say the second reading is coming out to be 18.12. And the third reading is coming out to be 0.7. Okay, you have something like this. Okay, then I am seeing that these 3 resistors are connected in series now. How are they connected? They are connected in series. So what is the operation you are going to perform? R series is equal to R1 plus R2 plus R3. When you add all these three, you're going to get a final output. Can you tell me what is the output going to be? Just do a quick addition and tell me what is the value.
$36.9.
How much is it? 36.9. You'll get 3 digits.
Oh, like fully answered.
Yeah, yeah.
95.
958.
Only 95, sir. The 7 and the 3 will get
Upper last only 950 upper answer.
950.
So 36.950 ohm is going to be the equivalent resistance when all these three resistors are connected in series. But you should not report the answer as 36.950. Rather, you need to round it off to how many decimal values? You need to round it off to
Least.
1 decimal value. So because among the three readings that I have, which is having the least number of decimal values, it is R3. So your final answer should not be reported as 36.950. Rather, you should write it as 36.
Sir, actually, 1 second, sir. I messed it up. It is 37.53.
37.535.
Okay, it is 37.535.
535.
Okay. Okay. So the output that we are going to get is 37.535, which has 3 decimal values. Whereas if you look at the readings that I gave you, the least one has only 1 decimal value. So you need to round it off to 1 decimal value. So how are you supposed to report the answer? 37 is fixed. Point. What is the number you are going to write after that is important. So you're going to drop this 35. So you're going to drop the 3. So what is the number preceding before it? It is 5.
5.
So when you're dropping a number which is less than 5, you will keep the preceding digit unchanged. So it is going to be 37.5 ohm. That is the meaning of the second rule that we need to follow. Are you able to understand that? The result should retain as many decimal places as that are there in the least decimal places of the readings that are given to you. Are you able to observe the real-time application of it?
Yes, sir.
Yes. So you will
Sir,
face this kind of. Tell me.
If there is like 2 numbers with the decimal places and 1 number without any decimal places, just integer, then what should you do?
Then you should report only the integer number.
Okay.
So next one is, there is a possibility where you will be asked to multiply or divide two values, right? So in any measurement, the last digit is uncertain. This we have been knowing from the definition of significant figures itself. So multiplication of any number with least significant digit is also insignificant. So you know that the last number in any measurement is considered to be insignificant. So when you multiply two numbers, right, that the ones place get multiplied. The ones place gets multiplied. No, so one insignificant is getting multiplied with another insignificant. So multiplication of any number with least significant digit is also insignificant, right? But we know that whenever you are reporting an answer, right, when you say you're reporting an answer, you're reporting it to the number of significant figures that particular reading possesses. So in that answer that you report, the final digit is considered to be insignificant only. If you give me any value, I will consider the final value as the final number as insignificant according to the definition. That's what the definition tells me. So, but the final result should contain only one insignificant digit. Therefore, to obtain this kind of an output, there are certain rules to be followed in the multiplication and division. The first one is, in multiplication or division, the final result should retain as many significant as that are there in the original number with the least significant. Meaning, It is the same thing that we have performed in the case of addition as well, addition or subtraction. It's the same rule. Okay. Secondly, when two numbers are to be multiplied or divided, and out of them which is not a measurement is a definite number. So the integers and fractions that occur in general in physics equations are definite number. I'll tell you what is the meaning of this. So let us see an example of the first case. The first case, suppose I'm asking you to find the area of a rectangle. So for you to find the area of a rectangle, for you to give me the output, what is that you need? You need the length and the
Length and the breadth.
Yes. Suppose I give you the length of the rectangle to be 2.613 centimeter and breadth as 1.2 centimeter respectively. So somebody who has measured length had a precise device. Somebody who has measured the breadth had less precise
Sir,
device.
it is 33.13.
Sorry, 30.
3.135. 1356.
But how will you get 33 pointer? 2 into 1 is
3.1356, sir.
Sir, 31.356.
31 varadu.
Wait, 3.156.
3.136.
3.135
1356.
centimeters square. Correct. So if you observe both the readings, which one has lesser number of significant figures?
1.2.
1.2. Right. Then how are you supposed to report the final answer?
31.1. I mean 3.1.
That is all you need. So how will you write 3.1? Because the digit you are trying to drop here is 3, which is less than 5. So answer will be 3.1 centimeters. Here, this is all you need to do. Similarly, there will be another situation where you will be asked to calculate the density. So density will be equal to mass divided by volume. So you'll have something like this also. So where mass is given to a certain decimal values, volume is given to a certain decimal values, you divide them, you get a final output. Right? Now,
Sir, like another doubt. If we have like two numbers with proper decimals, like 2 and 3 decimals, and the answer comes out to be like integer.
2 and 3 na 1 2 1 3 adu mariya. Can you give me an example? Can you give me a number which is there in your mind? Some random number. Some random number.
1.25 and 3.26, something like that.
Number 2 decimal na you will report.
Okay. Illa, the answer comes out to be like an integer. Like 00 vandiruchena.
But then you will write it as 2.00. That's it.
Okay. Done.
Yeah. Okay.
Okay, sir.
Yeah. See, actually, this point is just a statement. So this point is just a statement of what we have followed from the first step. So here I cannot give an example because they are only giving a statement. So all you need to do is whenever you're doing addition or subtraction, the rule is very simple. Addition, subtraction, multiplication or division, the rule is very simple. What is that you need to do? You need to round off the values to the number of significant figures that the least decimal value number is possessing. That's it. That is all we need to do. Okay. Am I clear till here?
Yes, sir.
Right. Okay. Next. The next important concept that we need to understand is, this is the last part of your chapter. Okay. But I promise I'll teach you the errors and everything also, but maybe later, which is not a part of your syllabus.
The parallax method and all.
That is all there. That is all.
Okay.
See, that is theory. That there is nothing for me to explain. That is all theory.
Okay.
Okay. So here we are dealing with numbers, no? That is why I want to stress on these points. And this is another important dimensions and dimensional formula. Okay. So if you observe, the name of the chapter is actually units and measurements. Am I right? Units and measurements. So for certain measurements that you're going to take, you're going to report the answer in terms of units. But the challenge with units is you have multiple variations. Like you have SI system, you have CGS system, you have MKS system, FPS, all these things are there, where there is a possibility where you might get confused, right? So in order to overcome that, what we can do is, you can report the answer in terms of something called as dimensional formula also, which has a parameter called as dimensions associated with it, so that the confusion actually comes down by a greater extent. If you ask me, is it something different from units or something? No, it is almost the same. Only thing is we get the idea from there, but it is just another way of representing things so that we try to decrease the number of permutations and combinations that is present. Okay, so by now we understood one thing. Whenever I talk about units, you have two types of units. What are they? One is called as the fundamental units and the second is called as the derived units. So you see, the physical quantities in this world are many. There are many, right? Obviously. When you have these many physical quantities, you are able to derive them from the fundamental quantities. So what people have done is they restricted the number of fundamental quantities in SI system to 7, so that it is easy for us to remember them, and you can do all the permutation combination to derive the other values. This we have already discussed. Like if I want velocity, what am I going to do? I'm going to divide the displacement with time. That is going to give me velocity. If I need acceleration, I'm going to divide displacement with time twice, so that I get displacement divided by t square. D is by, or d square is by dt. Sorry, I'm going to divide velocity with time, and velocity itself is divided with, velocity itself is written as displacement by time. So you combine them and write one final output. So I'm just giving you an idea of how to think. So if I give you a method where you have any physical quantity, which is basically derived quantity, there's not applicable, like dimensional formula is not mainly going to help us with the fundamental quantity, because we need to deal only with fundamental quantities. It is 7 or 10. For that, I don't need to find another method, right? Whereas if you talk about any derived quantity, that can always be expressed in terms of combination of the 7 fundamental or base quantities. So that's the outline, right? That is the objective of derived quantity, right? So now what we are going to do is, instead of we breaking our heads for understanding in which units am I supposed to present the answer, what I will do is I'll take certain letters for those fundamental quantities. For example, let's recollect what are the fundamental quantities that we know in the SI system. Mass, length, time, mass, thermodynamic temperature,
luminous intensity,
electric current,
amount of substance, and
the luminous intensity, right? So what I will do is, if I take that mass in terms of SI unit, it is measured in meter, whereas in CGS unit it is measured in centimeter. So instead of that, what I will do is, in the dimensional formula, I'll not be worried about which unit I'm trying to talk about. I'm only going to see the derived quantity that I have in my hand is how many times dependent on that particular fundamental quantity. Are you able to understand? For that, what I'll do is, for convenience, mass is denoted with capital M. So if you write capital M in a dimensional formula, the person who's seeing your paper will understand that you're trying to say that this particular physical quantity is dependent on mass. Similarly, you write L for length and T for time. Similarly, when you talk about electric current is represented with A. Okay. Similarly, the thermodynamic temperature is represented with K, and luminous, amount of substance in mole, and luminous intensity by CD. See, these three we use very less. Kelvin also use, but other quantities are little less, right? So, having said this, right, I hope you're able to get some perspective till here. I'll just give you an example. If I want velocity, So velocity is basically what? Displacement by time. So displacement is a physical quantity that is one minute. Yes. Yes. So your displacement is a physical quantity which is associated with length. So in the place of displacement, I will write it as capital L. And in place of time, I will write it as capital T. So then what will happen here is, can I write this as LT minus 1? Or I can write it as M0 L1 T minus 1. So if I give something like this to a person who's reading your paper, they understand that velocity is such a physical quantity, which is derived from the fundamental quantities in such a way that it does not depend on mass. Because what is the power to the mass? Zero. It does not depend on mass. Rather, it depends on the length once and time also once. But how is it dependent on time? It is reciprocal of time. So that is how somebody will be able to understand. And this way of representing a derived quantity in terms of these, what do you call it? These letters M, L, and T is what is called as dimensional formula. Okay, this is what is called as dimensional formula. And those powers you are able to, right? 0, 1, minus 1, they are called as the dimensions. So that is why the heading is dimensions and dimensional formula.
Sir, so dimension is the power of the base.
That number. Okay, now I'll give you the definition. Now you will be able to understand. See, so when a physical quantity is expressed with appropriate powers or exponents, powers means obviously you try to increase it by exponential values, right? Exponents of what? Mass, length, time, Kelvin, ampere. Then such an expression for a physical quantity is called as dimensional formula. So here, what is the dimensional formula? M0 L1 T minus 1 is a dimensional formula. And the power that you add to the physical, the power that you add to individual quantities which are participating in the dimensional formula, right, called as dimensions. The power or exponents of MLT are called as dimensions of that quantity. Right? The next question is, whenever you write a dimensional formula of a physical quantity, you generally put it with a square bracket along with the symbol of that physical quantity. Meaning, in velocity, generally the symbol we use is V. It is understood. So if you write in motion chapter, if you write somewhere, you write V. For example, if I ask you what is kinetic energy, you will say half mv square by default. And you already know that the m that you have mentioned, kinetic energy, is mass, and v that you have mentioned is velocity. You will not sit and write separately, tell me all those things. Suppose you write it as gh for potential energy. You are saying m is mass, g is acceleration due to gravity, and h is the displacement or the distance from a reference. Are you able to understand? So there are certain symbols which are used for the physical quantity throughout physics also. So meaning of it is, if I write something like this, meaning of this is the dimensional formula of velocity. That is what they told. No, the dimensional formula of a physical quantity is expressed by the square brackets along with the symbol of the physical quantity. You put the symbol inside, put a square bracket around it, and write the dimensional formula. So read it. Dimensional formula of velocity is equal to m0 L1 T minus 1. Clear with this? So this is the basic outline of what is dimension and what is dimensional formula. Okay. Similarly, just to make things simple, if suppose I ask you to write, the dimensional formula of acceleration, what will it be? So all that you need to do is do the rough work and see. Acceleration is velocity by time. So generally what I do is I write the units of it. I mostly write the SI unit. You can either write the unit or the definition. So meter per second by second square. So meter is related to length. So it is dependent on length once. It is dependent on time minus 2 times. So it will become M0 L1 T minus 2. So this is going to be the dimensional formula.
Sir, can you not do it like d by t by t? Velocity is displacement by time, so t by t.
That's what I'm saying. That's what I'm saying. It is up to you. I told you the way I think. But if you're convenient with something else, you can do that because that is rough work only. All I need is this value. You tell me that value correctly. That is important for me. Okay. Suppose I ask you what is the dimensional formula of kinetic energy. You guys try and tell me. So for dimensional energy, first write the formula, half mv square.
Sir, M1 L2 T minus 2.
Correct. ML2 T minus 2. Correct.
Yes, sir. Same answer.
Yes. So now write the dimensional formula for potential energy. See, capital U is generally used for potential energy. When I say potential energy, right, I can think of multiple things. I can think of gravitational potential energy, electrostatic, like this, many are there, elastic potential energy. We have so many, but whichever potential energy you remember, write and see. You remember MGH, no?
MGH.
Write for that and see. See, G is acceleration. If at all you don't remember, just giving you a hint. What did you get?
Sir, is it the same?
You will get the same. Because what is the prefix for both? Kinetic energy, potential energy. And what did you learn in your 9th standard? Energy is the capacity to do work.
Okay.
So find the dimensional formula of work done. Work done is force into displacement into cos theta. Cos theta has no dimension.
Sir, so every energy has ML2 T minus 2.
Okay.
It's fixed. So calculate the dimensional formula for work done. Meghna, Raghav, are you guys able to do?
Yes, sir.
So what do we do with the cos theta?
Cos theta has no dimension, right? It's just a number.
So just for
It's the same then.
You should get the same.
Same, yeah.
Because whether you calculate work done, see, for work done, what do we write? We write it as Newton meter, right? If you recollect, it is called a joule. So you will write kinetic energy also in terms of joule. You'll write potential energy in terms of joule, work done in terms of joule. Everything has the same unit. Obviously, they will have the same dimensions. Is that point clear?
Yes, sir.
Yes. So this is the outline of what is dimensions and dimensional formula. Now the next question that I need to answer is, now the next question that we are supposed to answer is, why are we even learning it? Or where is it going to help us? Is what we are going to see. For that, we have something called as dimensional analysis. So when I say something as analysis, right, we are trying to understand something mathematical. Right? We are trying to do a comparative study. Analysis is another. If I ask you to analyze something, I'm giving you an answer sheet. Somebody's answer sheet. I'm asking you to analyze whether the answers written in that sheet is correct or not. You're going to do some validation, right? Same thing. We understood that there is something like dimensional formula that exists. If at all it exists, is there any analysis I can do out of it, right? So the method of obtaining the solutions to several problems in physics by using this formula is what is called as dimensional analysis. That's true. We are going to use this dimension.
Sir, your voice is breaking.
Physical quantity in two different system of units. So it will help me to understand how to obtain the relation between the units of physical quantities which are measured. See, you have the same physical quantity, but their units are measured in terms of two different systems of units. One is measured in CGS, one is measured in SI, for instance. So at that time, I can use dimensional analysis. Second, to check the dimensional consistency of the equation connecting the different physical quantity. The meaning of this is, now you ask me a question, no? Sir, is it going to be the same? Like how are we able to say that the dimensional formula of everything is the same? Okay. If you recollect from your 10th grade, sorry, from your 9th grade, you would have learned something like this: work done is equal to change in kinetic energy. This is actually called as work energy theorem. What is it called as? It's called as work energy theorem. Similarly, if you have V is equal to U plus AT, you would have seen this also. I'm just telling you the equations which you already know. Similarly, you would have seen S is equal to UT plus half AT square. Remember, whenever you're writing a formula, which is basically called as a mathematical expression, whenever you're writing an expression, you will be able to equate two physical quantities only if they are dimensionally consistent. Meaning, whatever is the quantity that is there on the left hand side should have the same dimensional formula as that on the right hand side. Meaning of it is, the dimensional formula of V should be equal to the dimensional formula of U plus the dimensional formula of A multiplied with dimensional formula of T. See, that's obvious, right? What does V stand for? Final velocity. What does U stand for? Initial velocity. So at least the dimensional formula of these two quantities, directly we can say they are going to be equal. Whereas the third one, if you see, it is actually a product of acceleration and time. So what is happening here is acceleration has a separate dimensional formula. It is not the same as velocity. Time has some other thing, but the product of those two will be equal to the dimensional formula of velocity itself.
Okay.
If you write this kind of an equation, you say this equation is dimensionally consistent.
Okay. Sir, is there any equation which is dimensionally inconsistent?
You cannot write at all. See, for example, if you want to find something which is dimensionally inconsistent, make an obvious mistake. For example, if I give something like this is something which is an obvious mistake that I've done. Are you able to understand?
Yeah, so it is not possible to create.
You cannot write at all.
Okay.
So whatever mathematical equation, you learn it in the name of formula. You would have learned this as a formula, but basically, if you see, it's a mathematical equation. Any mathematical equation you write in physics should be dimensionally consistent. So dimensional analysis will help us to understand whether that equation is dimensionally consistent or not. If it is dimensionally inconsistent, and the equation, it's not possible. For example, I cannot write S is equal to UT plus half AT. It's wrong.
Okay.
Yes, that is the meaning of it. Because what is the mistake that has happened in this statement? I have the dimensional formula of velocity is equal to the dimensional formula of initial velocity plus I have the dimensional formula of displacement. I don't have for velocity. AT square is the dimensional formula of displacement.
Yes.
Meter per second square into time square is second square. Second square will get cancelled. You get meter, which is for displacement. Preda.
Yes.
It is inconsistent. So that equation is not possible at all. So
Oh.
that is the meaning of dimensional consistency, which is connecting different physical quantities. And the third help that it can do us is yes. And the third help that it can do us is you will be able to derive an equation for a physical quantity in terms of other physical quantities. For example, if this V is equal to U plus AT is there, no. You can actually derive this using dimensional analysis also. You would have derived this actually using the graph or the basic definition of acceleration. So A is equal to, you would have written it as A is equal to V minus U divided by T because it's a rate of change of velocity. Then you will take T to the other side, you'll write AT is equal to V minus U, which implies V is equal to U plus AT. You would have written something like this. This is from the definition, but there is a possibility where you can actually derive this using dimensional analysis also. So these are the three important applications of dimensional analysis. Okay, let's see each of them in detail. Okay, I'm going to slightly extend the class because it got delayed from my side. Okay. So you can write down this heading. So write down the heading. First, write the main heading as dimensional analysis. Under that, the first application. Okay. So in this, what we are going to see is, we are going to use dimensional analysis to obtain the relation between the units of a physical quantity in two different systems of units. For example, if I take unit of work in MKS system, that comes out to be joule. Whereas if I take the same unit of work in CGS system, it comes out to be in terms of erg. And what is the dimensional formula for work?
MLT L2 T minus 2.
So it is ML2 T minus 2. Right. Now what I'm going to do is I'm going to divide the page into two parts. One side I'm going to see for MK system and the other side I'm going to see for CGS system. So I'm going to see for MKS here and I'm going to see for CGS here. Okay. So in MKS system, mass is measured in terms of kilogram. Length is measured in terms of meter and time is measured in terms of second. Why did I take these three quantities? Because this equation is clearly telling me that work is dependent on these three physical quantities. So if I write the same thing in CGS unit, what I'll get is I can write this as 10 power 3 times mass. Why? Because in CGS system, the mass is measured in terms of gram. 1 kilogram is 10 power 3 grams. So similarly, the length here is written in terms of meters. So for me in CGS system, it should be written in terms of centimeters. So I should write it as 10 square times L in terms of centimeter. Whereas time, 10 power 0 times time in second. So if I combine everything and write no, left hand side I get ml t minus 2. Right hand side I get 10 power 7 times 10 power 7. 10 power 5 times 5 or 7.
Sir,
Yeah, 10 power 7.
L square, right?
L square. Yeah, I get 10 power 7. So 10 power 7 times ml square t minus 2. So what I'm trying to tell you here is 1 joule is equal to 10 power 7 times work. So that is the meaning of it. 1 joule is 10 power 7 work. So are you able to understand? We use the dimensional analysis to convert the unit of physical quantity from one unit to another, from one system to another, right? Am I clear with this?
Yes, sir.
You can make a note of this. Is it done? Are you done copying it? Okay. Shall we see the next application of it?
Yes, sir.
Yes. So the second application is to verify the dimensional consistency of a particular equation. To verify the dimensional consistency of an equation connecting the different physical quantities. Let's take the simplest example, and which is famous that you already know, that is F is equal to M into A. So if this kind of an equation is possible, then it is supposed to be dimensionally consistent. It is supposed to be dimensionally consistent. Meaning of it is dimensional formula of F should be equal to the dimensional formula of M multiplied with the dimensional formula of A. Okay. So what is the dimensional formula of F?
MLT power minus 2.
MLT minus 2. So LHS is MLT minus 2. Keep it aside. See, when you're writing MLT minus 2, you need not put that in square bracket. You can put it in normal bracket also. Whenever you put a square bracket around a physical quantity, you're trying to call it as dimensional formula of that physical quantity. So what is the dimensional formula of M? It is obviously M only. What is the dimensional formula of acceleration? It is LT minus 2. So MLT minus 2. Are you able to understand? So this equation is dimensionally consistent. This is a very simple example. Let me take another scenario also so that you will get more clarity. So I am saying F is equal to mv square divided by R. Check the dimensional consistency of this. So what is the dimensional formula of F? You already know. MLT minus 2. Right, this is for LHS. I'm not putting an equal to as of now. Now I'm taking this RHS and trying to solve it. For mass, what is the dimensional formula? M. For velocity, what is the dimensional formula?
LT minus 1.
LT minus 1. But LT minus 1 is raised to the power 2 because it's V square.
Okay.
Divided by R. R is radius, L. Okay. So if I observe the RHS, I'm getting ml square t minus 2 divided by L. This L will cancel this L square once. So answer comes out to be MLT minus 2. What is that you can conclude? F is equal to mv square by R is a possible equation because it is dimensionally consistent. I'm saying it is possible. I don't know whether it is right or wrong. It is possible. Okay. Are you able to understand? See, F is equal to MA, you already know. F is equal to mv square by R, you have not seen it till now. So that is why I'm very careful in telling what I'm telling. I'm saying it is a possible equation. But as you progress, right, when we go to further chapters, you'll be able to understand that this force is called as
Centripetal.
It's called as the centripetal force. As we progress, you'll see it because acceleration comes out to be V square by R. That is why it is M into V square by R. That V square by R is called as centripetal acceleration. M into V square by R is called as centripetal force. Clear with this? So now you got some idea of how the dimensional consistency works, right? Next. I'll do the last one. I'll explain it. Listen. The last one is about obtaining the equation for a physical quantity in terms of other physical quantities. For example, I say kinetic energy, right? Kinetic energy is a physical quantity which is dependent on mass and velocity. Okay, I'm telling you, there is some physical quantity called as kinetic energy, which is dependent on mass and velocity. So derive an expression for kinetic energy in terms of mass and velocity. If I put a statement like this, then all that you need to do is, I need to find the relation between kinetic energy, means my kinetic energy should be on the left-hand side, and mass and velocity should be on the right-hand side. But the challenge here is, I don't know how many times does my kinetic energy depend on mass and how many times does it depend on velocity. So what I will do is, I will say K is directly proportional to m power A, because I don't know what that exponent is, what the dimension is, and B power B. Am I clear with this? So when you remove the proportionality symbol, you introduce a constant. Let me call it as C. Okay, most of the cases we introduce K, but I'm using K for kinetic energy. That's why I didn't put it. So I write as K is equal to C into m power A into B power B, where C should be a dimensionless constant. What is the meaning of it? It should just be a number. Because nowhere in the statement, in the question they have given, the kinetic energy is dependent on the constant which we are going to introduce. We don't know. So if this kind of an equation is possible, then it should be dimensionally consistent. Meaning the dimensional formula of K should be equal to the dimensional formula of m raised to the power A and the dimensional formula of B raised to the power B. Why didn't I take the C into consideration? Because it does not have dimensions at all. Okay. So what is the dimensional formula of K? It is ml square t minus 2 is equal to, what is the dimensional formula of M? It is m raised to the power a. And what is the dimensional formula of B? It is
LT minus
lt minus 1 raised to the power b. So this will be equal to m power a, L power b, t power minus b. So after you have come to this step, all you need to do is compare the powers of the quantities, compare the dimensions of the quantities which are there on both the sides. Left hand side, m is raised to the power 1. So I can conclude, here I have 1. So 1 is equal to a. Similarly, I have 2 for the power of L. So 2 will be equal to B. And what about power of T? It is minus 2. Minus 2 is equal to minus B. So in either cases, B comes out to be 2. So the conclusion is A is equal to 1, B is equal to 2. So all that I need to do is take this and substitute it back in the first expression that we wrote. So what is that we can conclude, guys? We'll write K is equal to some constant times m raised to the power of a is 1, and v raised to the power of 2. So what is that you're getting? C times mv square. So kinetic energy is C times mv square. That is the problem with dimensional analysis. It can tell us that it is some constant times mv square, but it can't tell us what is the constant. Am I clear? Are you able to understand what I'm saying?
Yes, sir.
Okay, so this is the meaning of deriving a physical quantity in terms of other physical quantities. Is that clear?
Yes, sir.
You can make a note of this.
Done, sir. Sir, you are in mute.
The last point that I wanted to mention is, see, the limitations that we have with respect to the dimensional analysis. The first thing is, in any dimensional formula containing M, L, and T, we get at most 3 equations by equating the powers of MLT, because what I writing, you're writing M power A, L power B, T power C. So the number of unknowns in an equation is equal to the number of equations that you need to write. So in any dimensional formula containing ML and T, we get at most 3 equations by equating the power of ML and T. Hence, the method of dimensional analysis cannot be used to derive the exact physical form of any physical quantity that depends on more than 3 physical quantities. If at all you have any physical quantity that depends on more than 3 physical quantities, it is not possible for you to use this dimensional analysis to derive that expression. Is the point clear?
Oh,
That is one thing. Second is, we will not get any information about the dimensionless constant that we introduce. For example, in this problem, we got k is equal to c into the derivation which I showed you. We got k is equal to c into mv square, right? But we cannot find the value of c. That is only found experimentally. We know it now that c is equal to half mv square. That is, c is half. But we will not be able to know the same thing with the help of dimensional analysis. It will only tell us that there is some dimensionless quantity, but what is the value of it? Nobody knows. Okay. Third, we cannot use the dimensional analysis to derive relations which involve trigonometrical exponential and logarithmic function. For example, when I told you about work done is
cos theta.
displacement due to cos theta. Okay, but if I ask you to write the same thing using dimensional analysis, you cannot tell me whether cos theta is there or not, because it's a dimensionless quantity.
Okay.
So their dimensional analysis cannot be used to derive the physical quantity, the relation between the physical quantity. And lastly, this method cannot be used for those physical quantities where you have the constants which are not dimensionless. For example, if I ask you to derive this equation of f is equal to g m1 m2 by r square, unless you know that g is a physical quantity which has dimensions, you will not be able to derive this exact equation. Had you not known that g has dimensional formula associated with it, you would have not been able to derive. You will not get the answer as g m1 m2 by r square. Maybe you would have got m1 square m2 square by r. We don't know what you would have got. Are you able to understand what I'm trying to say?
Yes, sir.
Yes. So these are all the limitations of dimensional analysis. These are all the limitations that are existing with respect to the dimensional analysis. Clear with this?
Sir, but can you explain the fourth point again, sir? Like, force is equal to g m1 m2 by
Force is equal to g m1 m2 by r square, but g is introduced as a constant of proportionality.
yes.
So in dimensional analysis, what is the constant you are introducing? You are introducing a dimensionless constant. I told you that point. See, so whereas here, if I introduce g is not a dimensionless constant. It has units.
Yes.
It has dimension associated with it. Unless you know what is the dimension of that kind of a constant of proportionality, you will not be able to derive the relation.
Okay, sir.
That is the meaning of force. So that's what read the statement. This method is not useful if a constant of proportionality is not dimensionless. That is a meaning. Seriya?
Okay.
Okay. See, just to conclude the whole story, right? We have actually completed the mathematical part that is needed. The only thing is those measurements of how to do the parallax method and all those things. It's theoretical. Okay. So that part you can do a self-study also. But in my test, I generally don't test those parts. I will concentrate more on the mathematical part only, because I know that these are important for the subsequent chapters. Okay. So one point is I'm not available tomorrow, so there is no class tomorrow. Okay, I have some personal work. I'm not there tomorrow. So there is no class. So what will happen is you will get an assignment. Assignment is obviously going to be from the study material that is being given to you. Okay, in the study material itself, if you see the topics, right, under the topics, you'll have the topics of significant figures and you'll have the topics of dimensions and dimensional analysis. So those two topics, you can work on them and you can reach out to me if you have any doubt. And I hope everybody got a message about this, that after the class, after the holidays are over, you will be having a test. Did you all get that message?
Yes.
Got it. No. So what I will do is, for you guys alone, since you people are writing the 11th standard test for first time, before the class, before the test, I will hold another online session where I will specifically deal only with your doubts. So it is not necessary that you need to hold with your doubts till I hold a class. Okay, you have the student support number. Everybody knows the number for it, right? It is 6369210899. You have the student support number. So make use of it. Any doubt you have, post it there. I'll get back to you. Am I clear with this? Yeah. Tell me an yes or no. Yes. Are you clear? Yes. So start working on them, right? And I'll see you guys. So do the first test well. And you have any doubt, don't give up. Okay. Don't give up. Just reach out.
Okay, sir.
Okay. So that's it from my side. Any other questions that you have? Any other doubts in your mind?
No doubt, sir.
Is that all? Okay. So work on them. I'll see you guys.
Thank you, sir.